Imagine a world covered in ice. Estimates vary, but some scientists think at the poles it could have reached negative 130 degrees Celsius. And there was no escaping the cold even at the equator, where temperatures would have dipped below 0 degrees. Sheets of ice coat both land and sea, and beneath them, the world is quiet and relatively still. It may sound like some far-off planet, but that's what our own planet once looked like. And actually, it happened twice during a pair of episodes of intense glaciation between 716 and 635 million years ago. These global freezes occurred within the period of geologic time known as the Cryogenian, or time of ice, but most people refer to this chapter in our history simply as Snowball Earth. So how did this happen? How did the world become covered in ice? And most importantly, for us, why did the planet eventually thaw again? Strangely enough, for both of these questions, the answer lies in volcanoes. The evidence for Snowball Earth is written on every continent today. Since the early 1900s, scientists have been finding clues all over the world in the form of drop stones. These are rocks and pebbles that were picked up by glaciers as they moved across the land. And once the glaciers met the sea, icebergs broke off and floated away, carrying the rocks with them. When the ice melted, the stones dropped into the ocean. These drop stones show up in ancient marine formations all over our planet. And while the continents have shifted since the Cryogenian, scientists have been able to reconstruct the original positions of those ocean sediments using magnetic particles preserved in the formations themselves. These particles record the direction of the North Pole, which tells us where on the planet the drop stones originally fell into the sediment. And when you reconstruct where these drop stones were deposited, you can see that they stretched from the poles to the tropics, which means ice did too. Now we know that this extensive glaciation actually happened twice, between 716 and 635 million years ago. The first episode started 716 million years ago and lasted for about 36 million years. And the second lasted from about 650 to about 635 million years ago. Now, there have been glaciers on our planet before. In fact, we still have some now. But what makes these two periods so interesting is the extent of that ice. After all, today the tropics are pretty warm, a balmy 31 degrees Celsius in the afternoon, which is awfully warm if you're trying to freeze over an ocean. So how did our lovely temperate world get cold enough to freeze? Well, at first, scientists thought if there's evidence of ice having been at the equator, then maybe the equator wasn't actually at the equator. Maybe Earth had been tipped over on its side at some point, which would have made the equator part of the poles. That's how weird it was to find evidence of ice in the tropics. Scientists thought that it was more likely that Earth fell over than the equatorial oceans had frozen. But now we know that the evidence is too widespread for a change in Earth's tilt to explain it. In fact, the evidence is so complete that it's likely that almost all of the Earth froze over, including both the equator and the poles. Because in addition to drop stones, more evidence has been found in the form of carbonate rock. This rock is created when other rocks on the continents weather and break down to form ions, which eventually makes their way into the water. When those ions attach to dissolved CO2, they join together to form carbonate. And studies of ocean sediments all over the world have found that during parts of the Cryogenian, these carbonate rocks disappear. Because when the world was covered in ice, almost no weathering took place on land, so carbonates became really rare. But when the ice started to melt, weathering resumed, and huge deposits of carbonates began to form again. Most geologists think that the absence and reappearance of these rocks is a sign that Earth was mostly to completely covered in ice. But while that makes sense to the geologists, it doesn't make sense to some biologists. Life had existed on Earth for over 1 billion years by the time the Cryogenian started. And organisms like photosynthetic cyanobacteria and even animal life like sponges had evolved before the ice sheets grew, which raises the question of how early life could have survived under the ice. Some scientists have suggested that there must have been a fair amount of open, unfrozen water at the equator for life to persist. This model is called slushball Earth, but it doesn't line up with all of the geological evidence. So yet another hypothesis is that there was ice everywhere, but that it was thin enough in places for light to shine through and to allow photosynthetic life to survive. Studies of modern cyanobacteria in Antarctica suggest that life may have even thrived on top of the ice sheets themselves. But whether it was thick ice or thin ice, the ice was abundant. So then why did these massive glaciations actually happen in the first place? Well, the most popular theory is that our planet's thermostat just failed. That thermostat is the carbon cycle, the swapping back and forth of carbon between the atmosphere and the Earth's crust. And it starts with volcanoes, which over the course of thousands to millions of years gradually emit CO2 into the atmosphere, where it helps keep the world warm. But CO2 levels are kept in check because that gas gets stored in carbonate rocks from the process of weathering. So volcanic emissions and rock weathering are the two counterbalances that keep Earth not too hot and not too cold. But in the Cryogenian, an early supercontinent known as Rodinia messed with the thermostat by breaking up. Breaking up is hard to do, and rocks usually do it pretty violently. But the breakup of Rodinia was especially intense because it pumped out a lot of a volcanic rock known as basalt. And basalt is really good at soaking up CO2 in the process of weathering. Plus, Rodinia was sitting at the equator at the time, where it was warmer and wetter, which weathered the rock even faster. So scientists think that this could have thrown off the carbon cycle, soaking up CO2 faster than volcanoes could release it. And there was another contributing factor, the sun. During the Cryogenian, the sun was actually about 7% dimmer than it is today. Now, that doesn't sound like a lot, but it was enough that once the levels of CO2 dropped, it was so cold that glaciers started to grow. And in the last few years, scientists have discovered yet another driving force behind this phenomenon, a truly massive and spectacular eruption that took place 18 million years before the glaciation even started. Today, the remains of that eruption are known as the Franklin Large Igneous Province, more than 1,000 square kilometers of basalt lava that cover the Canadian Arctic. But what sets these rocks apart from others is that they were full of another planet-cooling gas, sulfur. When you pump sulfur into the air, it cools the Earth, but normally it doesn't do it for very long. Sulfur dioxide interacts with the water in the atmosphere and forms acid rain, typically leaving the atmosphere within a couple of years. But these eruptions weren't made by your standard volcanoes. Instead, they sprayed out huge jets of lava called fire fountains, which could have erupted for years, spraying plumes of sulfur gases up to 12 kilometers into the atmosphere. And that high above Earth's surface, near the stratosphere, sulfur dioxide would take a lot longer to break down and to rain out. So low CO2 levels let things cool down, and a dimmer sun didn't help. Then suddenly, 716 million years ago, vast amounts of sulfur dioxide may have been the final blow to Earth's thermostat, and ice began to form. The second glaciation may have had similar causes, but it isn't as well dated or understood as the first. But for both episodes, the real problem came when the ice started to grow. Ice reflects more light than water does, which makes the world cooler, which makes more ice grow, which makes the world even cooler, and so on and so forth. This feedback loop is called a runaway icehouse effect, and scientists who have modeled this process found that once our planet had ice below about 30 degrees latitude, the latitude of modern-day New Orleans, the growing ice was basically unstoppable. So why are we not still stuck on a world that's basically Hoth? Because of our old friend carbon dioxide. Rodinia didn't stop splitting apart just because it was covered with ice. As it kept breaking apart, volcanoes kept forming and releasing CO2 into the atmosphere. But this time, because the planet's rocks were mostly locked beneath ice sheets, they weren't able to absorb all that greenhouse gas, so instead it began to build up in the air. It took almost 50 million years for enough CO2 to melt the first round of glaciers, and about 10 to 15 million years to melt the second. Between the two glaciations, Rodinia continued to break up near the equator, which is why the thermostat broke twice during the Cryogenian. But by the end of the Cryogenian, Rodinia was largely in the southern hemisphere, and it had stopped splitting so dramatically, so the thermostat could reset itself. Once most of the ice had melted by about 635 million years ago, the warmer oceans suddenly began to fill with animal life. The period that immediately followed the Cryogenian, known as the Ediacaran period, is full of some strange and varied forms, descendants of the survivors of the Snowball Earth. But animal life itself didn't actually first evolve in the Ediacaran. Molecular clock analyses suggest the most recent common ancestor of all animal life lived long before that, some 800 million years ago, which means that somehow animal life actually lived through the Snowball Earth. How? Well, the earliest animals were practically unkillable, and it turns out they not only survived Snowball Earth, they helped change the oceans for the better. But that's a story for another time, so come back soon to learn all about the enterprising, trailblazing, and nearly indestructible animals that clung to life throughout the snowballs, the sponges.